Hi guys, today let's discuss the LeetCode question 96, unique binary search trees. Given an integer n, return the number of structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. So let's go to the example 1. So given the input n is equal to 3, the values of the tree node values can range from 1 to 3. So when the root is 1, there are two possible unique binary search trees that can be formed. When the root value is 2, there is only one combination that is formed. When the root value is 3, there are two combinations that are formed. So the output is 2 plus 1 plus 2, that is 5. And let's go to the example 2. When the input is n is equal to 1, there is only one unique binary search tree that is possible in which the root is 1. Yeah. I hope it is very clear from this question description. Let's go into the explanation part of it. When n is equal to 1, the number of unique binary search trees that will be formed will be 1. So that is going to be the root node of the tree. When the value of n is equal to 2, we can clearly see that there will be two unique binary search trees that will be formed. One with the root node being 1 and the other being with the root node equal to 2. When the value of n is equal to 3, we can clearly see that there are 5 unique binary search trees that are formed. Two unique binary search trees are formed with the root node being 1, and one unique binary search tree is formed with root node as 2, and two unique binary search trees are formed with root node equal to 3. Let's look at when n is equal to 4, the number of unique binary search trees that will be formed. When we look at n is equal to 4, we can clearly see that there are 14 unique binary search trees that will be formed. Now, by clearly examining all these n equal to 1, n equal to 2, n equal to 3, and n equal to 4, let's arrive at the relation of the number of unique binary search trees and the value of n. How can we find the number of unique binary search trees for different n values? Yeah. So here for the n is equal to 1, on the left subtree there is no node, on the right subtree also there is no node. So in this case, the number of unique binary search trees that are going to be formed will be 1 into 1. For n is equal to 2, on the left subtree there are no nodes, on the right subtree there is only one node. So in this case it is going to be 1 into 1 plus, for the root node equal to 2, on the right subtree we don't have any nodes, and on the left subtree we only have one node. So it is also going to be 1 into 1. So it is going to be 2 for n is equal to 2. So for n is equal to 3, on the left subtree for root node 1, on the left subtree we don't have any nodes, so it is going to be 1 multiplied by, on the right subtree we are having two nodes, 1 into 2, plus, for root node equal to 2, on the left subtree we are having one node, and on the right subtree we also have one node, so it is going to be 1 into 1 plus, it is going to be 2 into 1. Okay, let's look at for n is equal to 4. For n is equal to 4, in the first case it is going to be 1 into 5. 5 because there are 5 unique binary search trees that will be formed with the root node as 1, plus, for root node 2, on the left subtree we have one node, and on the right subtree we are having two nodes, so it is going to be 1 into 2 plus, it is going to be, for the root node 3 we are having two unique binary search trees on the left subtree, so it is going to be 2 into 1 plus, it is going to be 5 into 1. So it can be clearly understood from all these examples, like when for every n value we have to compute the number of unique binary search trees that will be formed for every n value. So if you look at n is equal to 2, we are computing for 1 and 2, and then we are summing it up. And when n is equal to 3, we are computing for 1, 2, and 3, and then we are summing it up. Same, we are proceeding the same step for n is equal to 4. We are computing for n equal to, for root node 1, 2, 3, and 4, and then we are summing up all these things. So I would request everyone to just give it a try and just go to the explanation one more time if you did not arrive at that formula that can be used to code this up. Let's start by creating a dynamic programming list to store the values of n. So we are going to initialize it with 0, and we are going, the length of that dynamic programming list is going to be n plus 1, and we are going to initialize dp of 0 with 1. The reason we are storing this dp of 0 equal to 1 is because whenever there are no nodes on the left subtree or right subtree, we are going to take it as a unique case. So that is the reason we are initializing it with 1. And let's loop through this for I in range of 1 to n plus 1, for j in range of I, and dp of I. So we have to add all the possible unique binary search trees in order to arrive at for each n value. So dp of I plus is equal to dp of j into dp of I minus 1 minus j. So we computed the value for a unique binary search tree value for every n value. Then finally, what are we going to do? We are going to return dp of minus 1. So dp of minus 1 is going to be the number of unique binary search trees for the value n. I think we are done. Let's quickly run the code. Let's quickly submit it as well. Yeah, it is submitted. Hope you liked the explanation. For more such videos, please subscribe to my channel. Thank you.